Hello, good morning viewers, students. I'm back here with a new topic and in a new format. In this lecture of mine, today I'm going to discuss one of the very interesting quantum mechanical phenomena known as quantum tunneling. This is Dr. Sudesh Jaswal, Associate Professor, University Department of Physics, TM Bhagalpur University. To illustrate quantum tunneling, we consider a ball rolling along a horizontal surface when it suddenly encounters a hill in front of it. Let the potential energy of the particle at the bottom of the hill be zero and its kinetic energy be E there. Similarly, let U naught be the potential energy of the particle atop the hill. Now, if E is greater than U naught, then the ball easily rolls over the hill and appears on the other side of it. So the probability that it passes over the hill is exactly equal to 1, and this is in complete agreement with our notion of classical physics. Now, let's consider the case when E is less than U naught. So in this case, the ball proceeds only part of the way up the hill, stops, and then returns in the direction it came. So the probability that it passes over the hill is exactly equal to 0, and the probability that it is returned back or reflected by the hill is exactly equal to 1. So we do not expect, even after repeated attempts, for the ball with E less than U naught to ever be found beyond the hill. And this is in complete agreement with our intuition about how the universe is supposed to work. Now let's consider a quantum particle, say an electron, proceeding towards a potential barrier. Now in quantum mechanics, a hill is characterized by a potential barrier, and this proceeds with a kinetic energy E. So in this case also, if E is greater than the height of the barrier, the particle gets transmitted through the barrier without any hassle. However, if E is less than U naught, the quantum mechanics here tells us an altogether different story. So quantum mechanics in fact allows the electron with even less energy, that means even if E is less than U naught, to tunnel through the barrier and appear on the other side. And this happens because of the probabilistic nature of the quantum mechanics, where we can't exactly pinpoint the position and momentum of a particle simultaneously, which comes from the Heisenberg uncertainty principle. So all particles in quantum mechanics are described by what is known as a wave function, which is defined over all space, and the wave representation of a moving body corresponds to a wave packet as shown here. The probability of a particle being observed at a particular location is given by the square of amplitude of the wave function. As a result, there is always a chance that as the electron encounters the potential barrier, it may suddenly be found beyond the barrier. This means that there is a certain probability that the particle will pass through the barrier to the other side, and a certain probability that the particle will bounce off the barrier. And this is in complete contradiction to our intuition about how the universe is supposed to work and has no analogy in classical physics. This is quantum tunneling. Now let's consider another illustration. So here we consider two metals separated by a thin layer of an insulator. Now, according to classical physics, on account of the energy gap, the insulator will act as a barrier to the flow of conduction electrons, and there is no flow of current across the barrier. However, quantum mechanics looks through the window of probability and finds that if the barrier is sufficiently thin, say less than 10 or 20 angstrom, then there is a significant probability that an electron which impinges on the barrier will pass from one metal to the other. And the experimental vindication also comes from the linear current voltage relation for junction of normal metals separated by oxide layer, which follows the Ohm's law. This is again in complete contradiction to our intuition about how the universe is supposed to work. So this is quantum tunneling. So quantum tunneling is a phenomenon in which particles penetrate a potential energy barrier with a height greater than the total energy of the particles. Quantum tunneling is important in models of the sun and has a wide range of applications, such as the scanning tunneling microscope and the tunnel diode. Emission of alpha particles from the nucleus and the field emission of electrons are examples of this tunneling phenomenon. You can see the process of tunneling in this particular animation. So here we have got a thin layer of an insulator separating the two metals on two sides of it. Now an electron is coming towards the barrier. This is the associated wave packet. As it impinges on the barrier, a part of it gets reflected and the other part gets transmitted. You can see the process of tunneling in this particular animation. So here we have got a thin layer of an insulator separating the two metals on two sides of it. Now an electron is coming towards the barrier. This is the associated wave packet. As it impinges on the barrier, a part of it gets reflected and the other part gets transmitted. Let's now enter into the analytical treatment or the quantum mechanical treatment of the problem. Here we have a finite height potential barrier which is described by the following potential energy function ux, where ux is equal to 0 for x less than 0, that means when we are in the first region. Ux is equal to u naught for x lying between L and 0, that means when we are in the second region, L being the width of the barrier. And Ux is again equal to 0 when x is greater than L, that means when we are in this third region. The energy E of the incident particle is indicated by this horizontal line. Now a potential barrier of height u naught creates three physical regions with three different wave behaviors. In region 1, where x is less than 0, an incident wave packet moves in a potential free zone and coexists with a reflected wave packet. In region 2, a part of the incident wave that has not been reflected at x is equal to 0 moves as a transmitted wave in a constant potential ux is equal to u naught and tunnels through to region 3 at x is equal to L. In region 3, for which x is greater than L, a wave packet that has tunneled through the potential barrier moves as a free particle in potential free zone. Now three situations arise. Number one, when the height of the barrier is infinite, then the wave packet representing an incident quantum particle is unable to penetrate it and the quantum particle bounces back from the barrier boundary just like a classical particle. Number two, when the width L of the barrier is infinite and its height is finite, a part of the wave packet representing an incident quantum particle can filter through the barrier boundary and eventually perish after traveling some distance inside the barrier. Number three, when both the width L and the height u naught are finite, a part of the quantum wave packet incident on one side of the barrier can penetrate the barrier boundary and continues its motion inside the barrier, where it is gradually attenuated on its way to the other side. A part of the incident quantum wave packet eventually emerges on the other side of the barrier in the form of the transmitted wave packet that tunneled through the barrier. Now, how much of the incident wave can tunnel through the barrier depends on the barrier width L and its height U naught, and of course on the energy E of the quantum particle incident on the barrier. Now the question is, what is the probability that an individual particle in the beam will tunnel through the potential barrier? The answer to this can be found by solving the boundary value problem for the time independent Schrodinger equation for a particle in the beam. The general form of this equation is minus h cross square by 2m d2 psi x by dx square plus ux psi x is equal to E psi x, where x lies between plus infinity and minus infinity. We assign equation number 2 to this. Now, in equation 2, the potential function ux is defined by equation number 1, this one. Now we assume that the given energy E of the incoming particle is smaller than the height U naught of the potential barrier, because that is the case which is of our interest. Now, knowing the energy E of the incoming particle, our task is to solve equation 2 for a function psi x that is continuous and has continuous first derivative for all x. In other words, we are looking for a smooth looking solution that can be given a probabilistic interpretation, so that mod psi x square is equal to psi asterisk x psi x is the probability density. We divide the real axis into 3 regions with the boundaries defined by the potential function in equation 1 and transcribe equation 2 for each region. Let us denote the solutions in region 1, 2 and 3 respectively by psi 1x, psi 2x and psi 3x. Then the stationary Schrodinger equation has the following forms in the 3 regions. In region 1, this is given by minus h cross square by 2m d2 psi 1x upon dx square is equal to E psi 1x. In region 2, it's given by minus h cross square by 2m d2 psi 2x upon dx square plus u naught psi 2x is equal to E psi 2x. And in region 3, once again, minus h cross square by 2m d2 psi 3x dx square psi 3x by dx square is equal to E psi 3x. Now the continuity condition at region boundaries requires that number 1, psi 1 0 is equal to psi 2 0, that is at the boundary between regions 1 and 2. Number 2, psi 2l is equal to psi 3l, that is at the boundary between regions 2 and 3. Similarly, the smoothness condition requires the first derivative of the solution to be continuous at region boundaries. That is number 1, d psi 1x upon dx at x is equal to 0 is equal to d psi 2x upon dx at x is equal to 0. That means at the boundary between region 1 and 2. And number 2, d psi 2x upon dx at x is equal to L is equal to d psi 3x upon dx at x is equal to L. That means at the boundary between regions 2 and 3. Now we can easily verify by substituting into the original equation and differentiating that in regions 1 and 3 the solutions must be in the following general forms. Psi 1x is equal to a into e raised to the power ikx plus b into e raised to the power minus ikx. Psi 3x is equal to f e raised to the power ikx plus g into e raised to the power minus ikx, where k is equal to 2me by h cross is a wave number and the complex exponent denotes oscillations. So here we have got the complex exponents, so they denote oscillations. Now e raised to the power, therefore e raised to the power plus minus ikx is equal to cos kx plus minus I sin kx. The constants a, b, f and g in equation 10 and equation 11 may be complex. Now in region 1 there are two waves. One is the incident wave and the other is the reflected wave which moves towards the left. So none of the constants a and b in equation 10 may vanish. That means both the constants a and b will remain there. In region 3 however, there is only one wave which moves to the right and which is the transmitted wave. So the constant g must be 0 in equation 11. So we can write explicitly psi incident x is equal to a into e raised to the power ikx. That means this is for the incident wave. Psi reflected x is equal to b into e raised to the power minus ikx. So this is the wave function for the reflected wave. And psi transmitted x is equal to f e raised to the power plus I kx. Now the amplitude of the incident wave is psi incident x mod square is equal to psi incident asterisk x into psi incident x, that is equal to a into e raised to the power ikx whole asterisk into a e raised to the power ikx is equal to a asterisk e raised to the power minus ikx into a into e raised to the power ikx, that is a asterisk a, that is mod a square. Similarly, the amplitude of the reflected wave is psi reflected x mod square is equal to mod b square and mod psi transmitted x square is equal to mod f square. Now we know from the theory of waves that the square of the wave amplitude is directly proportional to the wave intensity. If we want to know how much of the incident wave tunnels through the barrier, we need to compute the square of the amplitude of the transmitted wave. The transmission probability or tunneling probability is the ratio of the transmitted intensity, that means the ratio of mod f square to the incident intensity, that is mod a square. So TLE, that means this transmission probability or tunneling probability is given by mod psi transmitted x square divided by mod psi incident x square, that is equal to f mod square by a mod square, that is f upon a mod square, where L is the width of the barrier and E is the total energy of the particle. This is the probability that an individual particle in the incident wave will tunnel through the potential barrier. Intuitively, we understand that this probability must depend on the barrier height u naught. In region 2, the terms in equation 4 are rearranged to d2 psi 2 x upon dx square is equal to beta square psi 2x. I have rewritten equation 4 over here. Now where beta square is positive because u naught is greater than e, and the parameter beta is a real number given by beta square is equal to 2m times u naught minus e divided by h cross square. The general solution to equation 14 is not oscillatory, unlike in the other regions, and is in the form of exponentials that describe a gradual attenuation of psi 2x. As you can see from equation 16, psi 2x is obtained as c times e raised to the power minus beta x plus d times e raised to the power plus beta x. Now the three types of solutions to the stationary Schrodinger equation for the quantum tunneling problem has been depicted in this figure. So here we can see the oscillatory behavior in the regions 1 and 3, where a quantum particle moves freely, whereas in this particular region we can see the exponential or exponentially decaying behavior of the wave function. So here in this particular region, the particle moves in the potential u naught. Now we use the boundary conditions to find equations for the unknown constants. Equation 10 and equation 16 are substituted into equation 6. I have rewritten equation 10, 16 and 6. So when we substitute 10 and 16 in equation 6, we obtain a plus b is equal to c plus d. Similarly, we substitute equation 16 and equation 11 into equation 7. So this is equation 16, this is 11 and 7. So when 16 and 11 are substituted in 7, we get c times e raised to the power minus beta l plus d times e raised to the power plus beta l is equal to f times e raised to the power ikl. Similarly, we substitute equation 10 and 16 into equation 8, differentiate and obtain minus ik a minus b is equal to beta times d minus c by making use of the continuity of the first derivative of the wave function at x is equal to 0. Similarly, the boundary condition equation 9, which is the continuity condition of the first derivative of the wave function at x is equal to L, that gives us beta times d into e raised to the power plus beta L minus c into e raised to the power minus beta L is equal to minus ikf into e raised to the power ikl. We now have 4 equations for the 5 unknown constants. However, because the quantity we are after is the transmission coefficient defined in equation 13 by the fraction f by a, the number of equations is exactly right, because when we divide each of the above equations by a, we end up having only 4 unknown fractions: b by a, c by a, d by a and f by a, 3 of which can be eliminated to find f by a. The actual algebra that leads to the expression for f by a is pretty lengthy, but it can be done either by hand or with the help of a computer software. The end result is f upon a is equal to e raised to the power minus ikl upon cos hyperbolic beta l plus I gamma by 2 into sine hyperbolic beta l. In deriving equation 21, to avoid the clutter, we use the substitution gamma is equal to beta upon k minus k upon beta, where cos hyperbolic y is equal to e raised to the power y plus e raised to the power minus y whole divided by 2, and sine hyperbolic y is equal to e raised to the power y minus e raised to the power minus y whole divided by 2. Now we substitute equation 21 into equation 13 and obtain the exact expression for the transmission coefficient for the barrier. And this exact expression for the transmission coefficient FLE is equal to e raised to the power IKL upon cos hyperbolic beta L minus I gamma by 2 sin hyperbolic beta L into e raised to the power minus IKL upon cos hyperbolic beta L plus I gamma by 2 sin hyperbolic beta L, or the transmission coefficient T is equal to 1 divided by cos hyperbolic square beta L plus gamma by 2 square sin hyperbolic square beta L. This is equation number 22, where gamma by 2 square is equal to 1 by 4 into 1 minus e by u naught upon e by u naught plus e by u naught upon 1 minus e by u naught minus 2. It can also be proved that the reflection coefficient Re, which is the ratio of mod b square to mod a square, turns out to be 1 minus t, so that R plus t is equal to 1. Now for a wide and high barrier that transmits poorly, equation 22 can be approximated by this expression. TLA, or T as a function of LA, is equal to 16 times E upon U naught into 1 minus E upon U naught into e raised to the power minus 2 beta L. Whether it is the exact expression, equation 22, or the approximate expression 23, we see that the tunneling effect very strongly depends on the width L of the potential barrier. In the laboratory, we can adjust both the potential height U0 and the width L to design nano devices with desirable transmission coefficient. Viewers, with this, I come to the end of this lecture. Thank you very much. See you in the next lecture.